So let me share my screen. Can you guys see this rocket that I designed? Anybody please respond?
Yes, sir.
Yes, sir.
Okay, fine. So this is a small rocket design that I designed for you guys. So basically this rocket is created by cardboard section, and there is a nose cone at the tip, and there is some fins at the back of the rocket. You can see that, right? You know what's the components of a rocket. Basically, a body, a nose cone, a fins. That's a basic design. Okay. So you can see there is a tool I used to design this rocket, and also we can simulate the flight of the rocket in the software itself. So before we delve deep into the software, let me give you some intro. So we are going to deal with the design and simulation of rockets, as I must say. So first of all, what is a design? Can anybody can explain something about what is design?
A design is like deciding something should look before we actually make it.
Okay, that's a pretty good. So yeah, that's what Nandika, right? You're Nandika.
So it's Devik.
Okay, Dave. Okay. So as he explained, like design is something that we um, we plan before creating something. Okay, which explains the plan for creating something. There is some focuses on the purposes and the function and the different aspects of the product that which is going to come. Okay, and one of the major aspect of design is the communication of the concept, structure, and goals by visualization or text. So visuals like the last class you design something. So it's a visual representation of the design. Okay. So maybe we can say some mathematical formulas. Maybe we can say about the dimension and things. That's a textual representation. So design have both visual and textual representation. You can see we all try to draw so many graphs in our school works. So it's all like a visual representation for communicating some concept or structures or anything. Yeah. So that we can call as designs. Okay, is that clear to everybody?
Yes, sir.
Okay,
Yes,
fine.
sir.
So now we can move on to simulation. So anybody, again, I'm asking what about, just know about what is simulation.
Sir, simulation is creating a model by running experiments on it.
Okay. So simulating is something like experimentation. So if we create some kind of model or a design of something which is going to come or something we have to prove, we have to simulate under different terrains, different aspects. Okay, so if we create something in a real world, we have to test it somehow. But if it fail, it completely fail. We have a lot of losses. We have financial losses. We have uh, labor losses. So many losses that we are going to occur. So to avoid so many complications, we have to simulate the designs or the models or the prototype that we create before the actual product. So it may be computer based, it may be other experiments. So if we create a prototype, we can use, yeah, let's take an example of a um, rocket or aeroplane or whatever it is. We simulate so many environment that this plane or rocket going through in so many places like high pressures, so many different temperatures, in everything in some chambers called flight simulation chambers or something like that. Okay, you so I wish you understand what is actually a simulation. Okay, it's something that we do before creating an actual product by imitating the real world aspects which is going to occur in the future on the same product. Okay, so I just read it. Imitation of real world processes that might occur over some parameters. Okay, so there is some parameters like time and maybe over the distance, maybe over temperature, maybe over the pressure. So we can get the imitation of the real world processes. Okay, and now you can see that computer based models are there. Maybe we can use wind tunnel chambers are there. So it's a actual case and computer based as a digital case. So which is like simulation. We are going to deal with simulation also in this lecture. Not as a lecture, it's a series of things, and we you learn with us by doing the things. Okay. So why we need simulation actually? Let's take an example of a motion of a car. You know, um, is is everybody is from 11th or 12th standard? Or can anybody answer that? The students from 11th and 12th standard? Okay. Can you guys hear me? I wish I can.
Yes, sir.
Okay. Is there anybody from 11th and 12th standard?
Yes, sir.
Okay. So guys, you know motion equations, right?
Yeah.
Yeah, motion equation actually applies to straight line motions.
Yeah.
Okay. So when we deal with motion equations, so for the students below that, motion equations are equations that we can use to predict the future events with respect to time. So there is speed. So when a car moving through a straight line, uh, road or something, whatever, it has some speed, or we can say velocity, and it covers some distance, and it may have some acceleration. So with respect to time, the velocity, acceleration, and the displacement or distance, it changes. But the motion equation allow the observers like us to predict the future, how the velocity, how the time, how the distance or displacement changes over the time. Okay, but in some cases, the car not moves in a specific way. In actual cases, in most of the actual cases, the car don't move like that. Let's take an example like let's a car is going in a way, in a straight line way. If there is a lot of highs and bumps, the car had to constantly reduce its acceleration, so it reduces the velocity. So again, it comes to a perfect path. It again increases the acceleration. So there is a lot of fluctuation in the acceleration and the velocity. So it's the motion of the car. It's not become perfectly. So we cannot use the actual straight line equations. So we have to do more complex analysis on the car, which is we have to analyze on the micro level. Let's say uh, at the instant of time, we have to calculate what is the acceleration, what is the velocity, what's the distance and displacement. And we take in another instant of time, we have to calculate there the velocity and acceleration and the uh, other parameters that are associated with it. So it become more complex. In the simulations, we also doing the same thing. There is lot of parameters that might come for the object. For specifically taking the rocket, there is lot of parameters like altitude, pressure, temperature variations, and many other parameters. So all the time or any other aspect, these values may be changes. That's not maybe linear. It's not linear. In actual cases, it's not linear. It's highly fluctuating. So if we want to calculate the right altitude, the right uh, temperature, the right pressure, it's everything. If we want to calculate, we have to constantly calculate at each point. So that's what we are doing in simulations. So for doing the simulations, we need uh, powerful computers, powerful machines, because they consume a lot of power and they need so many capacity to run that simulations. But for the applications that we use, it's a common and it's basic. So it can run on platforms like so laptop and things. So today lesson section we are going to plan that I will be making a model rocket and we deal with stability of the rocket, and we also simulate the flight path and the altitude and the drifting of the rocket. So the lecture will be same as the designs lecture, that you guys cannot do design with us because it's a lot of time consuming. So before going to the application, let me give you something that you have studied as I said, guys, that we are going to use the simulation software called Open Rocket Simulator. Open Rocket Simulator is a free open source uh, software which we can use in our laptops and things. So it's not expensive and it's also open software. So before going that, like these two concepts, the center of gravity and center of pressure. Have you guys studied about the center of gravity and center of pressure in the previous lectures? Okay, I'm getting any responses. So let me just, I think Abraham has taken care of this. Like, let me give, just read this thing. Like, the points where the whole weight of the body assumed to acting. Okay, the center of gravity, where the entire weight of the body assumed to be acting. Okay, that's the point. And the center of pressure, the points where the whole aerodynamic pressure assumed to be acting. When a rocket or when an aeroplane going through air, there is a lot of aerodynamic forces that act on the body because of the air and the wind that act on the body. There will be a lot of pressure creating. So the entire pressure we can assume to be acting at that point. So at that point we call it center of pressure. Okay. So for stability, the center of pressure should be behind the center of gravity. So you guys knows about this picture? Anybody knows about this picture? Or what it is representing? Which game is it representing? So it's basically a dart game. So there is a dart or projectiles you can pin to a marking board. So for this particular object, the mass of the projectiles are concentrated at the tip, at the front tip, at this portion. The mass are concentrated at these portions, and the back so many feathers, as you can see. So which creates more stability for the dart game, for the projectiles. So that's why the design is like this. For the rocket also, the design is similar to this. So we can go and make a design like this. So for stability, the ratio of distance between the center of pressure to the uh, center of pressure and center of, I think I missed something here. The ratio of distance between the center of pressure and the center of gravity to the diameter of the rocket. We can see this in the open rocket simulator when we design this. So this is the basic parts that we are going to design through the open rocket simulator. So you can see there is a lot of parts of a small rocket. So first of all, I will give you this part, the red part, which is the nose cone. Okay. And the second part in this large tube, this is the body tube of the rocket. And this portion is the engine. Engine. This portion is the engine portion. So there is a engine block, and behind the engine block there is a centering ring, and at the back there is a engine motor. So on the side you can see fins. So on the last you can see the parachutes which is coming out. So if you guys really interested learning designing and simulating. You can watch, you can go and understand basics of simulating and also the general concept of the rocketry. You can use, this is our YouTube channels that I have used, Lab Rat Scientific and the Rocket Nuke. So, what about the concepts that we studied? Is it clear to everyone?
Yes, sir.
Okay, fine, fine, fine. If anybody having any issues, please let me know. So, without wasting time, we can go home design. So, as you guys saw that, this is basically the 3D view of the rocket that I have designed for you guys. And you can see we are first of all going to get the environment of the software. If you can download the software from the Google over, or if you, as I mentioned, it's a free and open source, so you can download it directly from the Google. Okay, so this is the main environment of the software. So as you can see, there is three sections. At the top, there is three sections. The first section is rocket design. So for the rocket design, here we design the entire rocket. Okay. On this section, we design the entire rocket. So if we say the sustainer, which is a pre-built, if we just click in sustainer, you can access the components right here. And okay, so you can add so many components to the sustainer section. Okay, so this is the first section for the rocket design, and the second section is motors and configuration. For the motors and configuration, so you can see when I select the motor and configuration, there is a red area which is pop up on our design, which is actually the motor area. So we here we can select so many motors. What is actually a motor is? A motor is a engine, let's say engine, which is propels, which is thrust the rocket upwards. So basically, the open rocket simulator deals with solid propellants. So if we want to use liquid propellants, we have to externally add by other means. Some other Python programs are there, and we have to um, pre-build the liquid rocket engines and configure that into the um, open rocket simulator. Basically, the open rocket simulator deals with the solid rocket propellants. Okay. So the next section is the flight simulation. If we go to flight simulation, you can see there is a lot of simulation that I have tried to run. So if I select simulation 3, it's not quite responding to me. So I'm trying to plot something like on a graph of the third simulation. Let's try that. So here I selected the third simulation, and on the second box you can see the flight configuration. Flight configuration actually which motor which I have to select for the particular simulation. So I can select the motors here, and we can go like no. So we can discuss the launch conditions later. So plot data on there is an x-axis. I can select so many variable which I can run on x-axis. As you can see, there is a lot of variables on the x-axis. So let's take a time on the x-axis. So on the y-axis, I'm going to take altitude and the position of motions. I can select the altitudes. So if I plot this, I will get how the rocket altitude varies with the time. So I'm going to plot. So which is actually the simulation. As you can see, guys, on the x-axis there is time. On the 0 time, there is no altitude, and get to maximum apogee at around 1.78 seconds. Okay, so then finally comes down slowly, slowly, slowly. It comes down. You can see there is a declined motion, and up to 25 seconds it will be flying. Okay, this is what the simulation. We have simulated the path, not the path, the altitude of the rocket that I have designed. So, guys, we can design a fresh rocket from somehow. Is everybody to So, guys, is everybody ready to build a rocket? Please respond, guys.
Yes, sir.
Yes, sir.
Okay. So, I wish so far so good, right?
Yes.
Okay. So, first of all, when
Yes,
we
sir.
open,
Yes.
Yeah.
okay. First of all, when we open the application software, this is the window. Then we can go for preferences because you see there is an edit. So we can go for preferences and we can change enough parameters for us to understand. So you can see there is a lot of parameters that defaulted in the systems. So basically I'm going to units. So you can see rocket dimensions are in centimeters and motor dimensions are in millimeters. So there is a lot of contradiction between the dimensions that they use different dimensions. So what is comfortable for you guys? You can select the dimensions according to your preferences. Okay. So why motors are in is because we can get the motors from the building, like so many manufacturers are there building motors for the rocket propulsion. So we can take their motors into our build, into our rockets. So for a universal specification or a engineering specifications, millimeters are the standard units. So that's why the motors dimensions are in mm. Okay. So you can change the preferences according to you though. So here is a lot of material list. You can see there is a lot of material list next to the unit. These are the materials that we can use for the different components that we are going to build in the rockets. If you want to add specific components from yourself, you can add here. Okay, I shall leave all of this like this. So we are going to create our pockets. So when I selected the sustainer, you can see there is a lot of components that comes on the right side. So first of all, we are going to start with the nose cone. This is the nose cone. When we just click on the nose cone, there will be some window will pop up. So this window is a choose component preset. So you can see there is a lot of nose cone which is available in the market, which is from so many manufacturers. Like you can see the manufacturer here, Apogee, Balsa manufacturers. So many manufacturers are already manufacturing so many nose cone. So if we are buying the particular nose cones, we can just use the presets from here. So mostly these companies, these manufacturers are from America. So we cannot use this here in India because it's very expensive to buy this product from America to India. So we just close these windows and we can create our own custom nose cone here. So first of all, for a general, the nose cone have different kind of shapes. You can see here a lot of shapes like conical, ogive, ellipsoid, oversized, parabolic, and so many shaped nose cones we can simulate or design on simulation. We are now designing. So I'm just going with ogive, and you can change the shape parameters, and also you can change the length, the base diameter, and what's the wall thickness and everything. So for the length, I'm just taking the 15 centimeters, and the base diameter is 5 centimeters. Okay. And here you can see the wall thickness, which you can select as your preference. So if you want to just dive, we can just dive this here. So which is automatically changes the wall thickness. Or you can just come here and just this 0.2 centimeters. Okay. So on here on this side, you can see the material. So which material we can use on the nose. So there is polyester. So if you selected that, there is a lot of materials that we can use for the nose cones. So I'm just going for like plastic products that we can use easily 3D printing products like plastic, IPC or PLA, which is mostly available and we can easily manufacture. PLA is the material that I have there. Then if yeah, on this part there is, you can see the component finish. So when we manufacture anything, nose cone or shoulder or whatever on the rocket or anywhere, there's a lot of finishing. If we really sand it and sand the product, like sanding is means the rubbing with sandpaper and make it the product smooth. Okay, so when we smoothen the product more, especially the nose cone structures, it will create a lot of less resistance to the airflow, which will substantially increase the aerodynamic performance. So we had to uh, select the components, what type of smoothness, what type of the finish that the product have. So I'm just going with the regular paint, 60 micrometers. Okay. And so you can see, yeah, this is all the parameters that we can change. We can change on the mouse cone, and you can see there is a mark, the flip to tail cone. If you just mark it, there will be a section comes on the end side of the cone. Okay, you can see I just flipped. We don't need to that. Okay, then there is the field. If we just if you just click on the field, the entire nose cone is a solid. Okay, so for the nose cone, you can see how the nose cone comes here, how the nose cone looks here, and there is a lot of other customs that we can make on this. There is a appearance structure. Here we can change the color and the component color and opacity and shining in something like that. So he doesn't need to care about that. So one thing that we have to use, there is a shoulder. So every nose cone there should be a shoulder. Why we need a shoulder is when we attach the nose cone to the main body of the rocket, we should need a shoulder to fit into the main body of the rocket. So when we add the main rocket, you can see how the nose cone going to fit inside the main body. Okay, so I'm going to select. I'm going to give it some dimensions for the shoulders. I'm going to give a 4.6 diameters shoulder, and the length will be around 3 centimeters. And as you can see, there is a shoulder comes out from the nose cone. Okay, so I'm going to select the thickness also and put 2.2 centimeters. All right. So there is also a filling the end cap. So what is end cap is the end of the shoulder will be covered. If you want to cover the end, we can just tap on the end cap. So the end will be covered. Okay. So we just designed a nose cone for the rocket. And as you can see, when we design the thing, there is 2 points. You can see 2 points are there. So one is the red point and one is the blue point. So what is these points? Here you can see a blue point, which is center of gravity, CG. You can see that here, the center of gravity. Okay. And the red mark is CP, which is the center of pressure. So the software or the simulator or whatever, they are constantly calculating what should be the center of pressure at the center of gravity should placed or should assume to be placed by when we add some weights or when we add some stretches. Okay, so when we add the body tube, the weight will increase, so the center of gravity will change. When we add a the tip like nose cones, the performance will be changed, the aerodynamic pressure will be changed, the center of pressure will be changed. When we add some fins, the aerodynamic performance also will change and the center of pressure will be changed. So when we adding different parts of the rockets, the center of pressure and the center of gravity will be changes. So it's fluctuation. But we need something, a magic. A magic is there. So this is the magic thing, that the stability. So we discussed about the stability, right? We discussed the stability is the ratio of the distance between the center of pressure and the center of gravity to the uh, diameter, that's this length, the diameter of the rockets. Okay, that's how we calculate the stability. So as I said that if we need more stable rocket or more stable, which is stability, which is means that the rocket should fly or rocket should flux through like in the air in a very straight manner. Okay, so the parameter stability which decide it should goes on the straight path or it should go like deviate to the one side or deviate to the side or rotate or about the axis perpendicular. So we don't need anything like that. We just need to go the rocket in a bit straight path. So that's where the stability comes. Okay. So for the stability, we have to make sure that the center of gravity always is above the center of pressure. Okay. And also we are going to aim this stability. The ratio will be around 1.5 to 2. Okay. So we can do that by adding so many components in the fins. So first of all, we are going to add the body to the sustainer. Okay. So I'm again selecting the sustainer and I'm going to select the body tube. So as you can see, there's also a preset comes. There is a lot of manufacturer which produces the body tube, but we don't need any presets. We are going to create a button. So there is, oh no, I think there is a two body. Sorry, we don't need to. Okay, I just deleted the second body tube. So this is the configuration window for the body tube. So we are making a custom body tube. As we see on the nose tube, here you can see how much length we need for the body tube. Let's take a 50 centimeters or something. So I take a length of 50 centimeters, and there is the outer diameter. So the outer diameter is 5 itself because we have set the diameter for the nose cone 5. So that's automatically comes on here. So I just select on that here. And you can see that the inner diameter. So the inner diameter end wall thickness. So the inner diameter should be matched with the shoulders because the shoulder had to be perfectly fit into the body tube so that the inner diameter should be aligned with the shoulder of the nose cone. Okay. So here's also you can see that materials, which type of materials are we are going to use for the body tube. Why we are selecting the materials? Because the computer analyzes the weight from the component materials. Okay, that's why we are selecting materials from the uh, configuration menu. So here's also you can see the component finish. You can see there is a lot of component finish, as we said, how much it is finished, how much it is smooth, how much it have smooth. So which really influence the center of pressure because it's the amount that the aerodynamic forces acting on the body. Okay. Here also we can see the appearance, we can change the colors, we can change the opacity and shine. So we don't need this tool. Okay. So we got the main structures, the nose cone and the body tube. So now you can see that the center of gravity is shifted so backward because the weight is increased, but the center of pressure is uh, very high. So this structure is not a stable structure. Okay, if we need to create the stable, the center of pressure should lie below the center of gravity. Okay, for making that, what we can do is we can add the fins. So I again go for the sustainer. Okay, so I go to sustainer. You can see I cannot select the trapezoidal or elliptical or freeform. These three are the fins. These three are the major fins. There is a two fins which we cannot use that right now. So if we want to select and work on the uh, for fins, we have to select the body tube first of all. So the fins will come on the body tube. Okay. So I selected the body tube. Then I'm going to select any type of fins. So basically, most of all the fins will be trapezoidal. So I'm going to select these trapezoidal fins. I just select the trapezoidal fins. The configuration menu will come. As you can see, the first in the general section, the first thing is the number of fins. How much number of fins that we need. So basically, we are going to use four. That's more stable. Okay, sorry. We can use four fins. Okay. And there is a fin can. So the fin can is the how much angle we can tilt the uh, fins. So if I increase or decreases, you can see the fins will look in an offset. Yeah. The fins will look as a tilted. Okay, but for tilted fins, it is not stable. So we don't need a tilted fins. So I just keep it 0. Okay. So then you can see the root code. The root code is the length that the uh, fins which will attach it to the body of the rocket. So just selecting, can you can see 7 or something. So you can see that the tip code is sorry, the root code length is increased. We can also change the tip code, maybe 6 selected and rate. And also we can change the height. We can change the height to some values. Uh, and the seep angle, seep length. You can change so many parameters over here and how you can perform how the center of gravity, center of pressure will be changing. You can change these kinds of parameters when you actually download and experiment in this applications or in the software. Okay. There is also something fin cross section. There is you can select rounded fin cross section, aerofoil, square. Square. We basically go with the square and what might be the thickness. We can increase the thickness because it should be very rigid. It won't snap off. Okay. You have to make sure that it won't snap when the actual flight occurs. So you can select the thickness, whatever it is. And here you can see the material components. Okay, here we can see balsa, which is a wood material. So when we go for woods, we can see so many materials right here. I'm going to select balsa. Yeah. Also, you can see the component finish, which also related to the center of pressure, and the root fillets. So the root fillet is the tip. You can see the tip of the fins. Okay, if the tip of the fins is rounded, that's what we call fillets. So the fillet round or fillet radius you can change, which will also affect the center of pressure because it's create more stability. Like center of pressure will be reduced backward because the center of like the forces acting on the body is less. Okay, so the fillet materials also balsa and the components and everything. And as here you can see on the iron or the information section, the component mass is 5.3 grams. Okay, 5.3 grams would be the entire mass for the four fins. This is calculated by the component material that we have given. Okay, and if you want to cut the fins, we have to manufacture the fins, right? So if you want to cut the fins, what we can do is we can export this to SVG files. So SVG files is the drawing files. Okay, so these files we can use for laser cutting or plasma cutting or any other cutting. We can use the exporter SVG files and we can cut the exactly same um, dimensioned fins. So we can export from here the SVG files. Okay. I'm going to give the tick will be around 10. That's fine, I guess. So there is something we can do. So you can guys, yeah, we have changed the root code by manually. So if we select to convert to freeform, there will be something like on the freeform, you can see the shape. We can change the shape by the graphs. Okay. You can manually change this. You can manually, if you just select at this point, you can manually change the shape of the things according to your preferences, how you want to do this. Okay. So which will reflect on the mouse. Fine, I guess this is fine. So I just okay. So now you can see the finished form that now we have a nose cone and now we have a body tube. Then also we have a fins. Right now, our body stability increased so much because you can see the stability is 2.99. As I mentioned earlier, we only need 1.5 to 2. So which is very stable. Okay. But the design is not completed. There's a lot of components are going to come. We can see the center of pressure is below the center of gravity. Okay. So now you can see the rockets in a form like if you want to see the entire part of the rocket, here you have a slider and you can slide the rocket so the rocket will rotate. Okay, as you can see, the rocket will rotate. So if we keep it this direction, so we'll say if you want to change 180 degrees. So this is a basic rocket structure. We have designed a basic rocket structures. Okay. Now we need to add some motors, which is the propelling unit. As I mentioned earlier, the solid propellant is basically we are going to use on the open rocket simulator. So before we are getting a motor or the propellant, we have to make a platform where the propellant can set. Okay. So first of all, I'm going to select the body tube. I'm going to select the body tube. So when I scroll down here, you can see there is a inner tube. So if you select the inner tube, the inner tube will come on the main body tube. As you can see on this section, there will is a inner tube is. So it's also a lot of presets. We don't have to deal with the preset. So we can change the length. We can change the outer diameter, inner diameter. Okay, we can change the wall thicknesses. So what I try to do is before we configure the inner tube, we can also add some motors. Okay, I just created a inner tube and I'm going to the motors and configuration and I'm going to select one of the motor. So the motor will be going to mount in the inner tube. So I selected the inner tubes right here. Okay, so here is a configuration and to the inner tube. So I'm going to select a new configuration. So here we can see lot of, as you can see that is lot of solid propellant, so the motors. So I can select some motors from the manufacturer. So when making some motor, it is pretty hard to make a motor. Okay, so we just uses the already existing motors that made by manufacturers like Estes and Coasters. Like these all manufacturers from America, but we can find a similar motors in India like C6 and C5, something like that. You can find out these motors in India as well. So there is you can see the name. So the name is B4, B6, B14. So many names are there. So which is actually a name for the motor. There is a code for the motors. That's what the name actually specifies. So the first letters are the power, how much thrust it can produce, and give you the complete details about the motors. So the first letter of the motor explains about the energy, how the first letter, the total energy or the impulse, the total energy or the impulse it might have. Okay, the first letter is talks about the energy, and the second letter is mostly talks about how the average thrust it can produce, how the average thrust the motor will produce. That the second number page. And for some, okay, okay, we can see, yeah. So when we select any of the motors, we can select any motors. We can like change the total impulse. You can, as I mentioned, that the ABCs stand for the total impulses. You can select the just the total impulses. So when we increases to A to O value, the total impulses also will increases. Okay, we don't need so many impulse. But for here also you can see the motor dimension. The motor mount dimension is 80 mm to 17 mm. So which is the standard unit, the variations. So you can see the nominal diameter, and also you can changes the length that we are trying to get. So here I just select some of the, which should I select? And in 98 centimeter line, I'm going to select something like 7 centimeters. Yeah, so I'm going to select something like uh, F30 or 41 something. Okay. So here is something called ejection charge delay. So ejection charge delay is a second is a time period after the ignition completed to the parachute deployment. Okay, so you got it. The ignition charge delay is the time delay from the motor ignition completed to the charge delay, which is charge delay is actually is the parachute deployment time. We have to recover the um, rocket by parachute methods. So there should be some charge delay. So even if the motor completely burned out, there will be acceleration. So there will be a motion. Okay. Sorry, there will be a speed or velocity the rocket might have. So it will move further away even after the complete burnout. Like let's take an example of a human running in the speed. Even if we try to stop somewhere, but he will eventually stop in another distance. Like there will be a stopping distance between the actual stopping and the uh, like decreased acceleration. Okay, so we can increase the time to 8 or something because we don't need to reduce the ignition like parachute time. So we can get the ignition delay time to 8 or something. So I think it's all set here. We select the motor. It having counts here. we are inserting motor. I couldn't select the motors. Oh yeah, now it comes. The motor comes. So now the motor is here. So we can change the rocket. We can go back to the rocket design. Then change the dimensions of the inner tube which we prepared. We can increase the length. I'm having a little trouble with the internet connection. I guess it's not doing fast. So we don't need for 15, we just need maybe 13 or yeah, 13 is fine, I guess. And the outer, we have to increase the outer diameter. Okay. So I'm increasing the outer diameters and I'm trying to reduce the inner diameter. So 2.7 is fine, I guess. 2.7 is fine. We have to increase the wall thickness to 0.2. So now you can see the centering ring is perfectly fit, that the motor is fit on it. Okay. This also you can change the material of the uh, inner tube. You can change the material to cardboard or plastic or whatever it is. I'm just going with the cardboard itself. So it is completed. Now you can see that the inner tube is freely flowing. It just sits there, but we don't need that. We have to make sure that it's perfectly fitted on the body. So I'm again going to select the inner tube and I'm using some centering ring to center the inner tubes. So I use the inner tube and I selected the centering. There is a presets comes and we don't need presets and we're going to be configured the centerings. So as you can see on the tip, there is a centering comes. We can change the positions of the centerings by changing here. So the centering will move according to what the positions we are trying to place. Okay. Then here you can see the thickness for the centerings. If you want to increase the thickness, you can increase the thickness. It will increase the thickness of the centerings. As you can see, there is the thickness is changing, and we have to maintain the outer diameter of the centerings perfectly to the outer diameter. Sorry, the inner diameter of the body. So 4.5 is fine, I guess. 4.6 is fine. Okay. And also the inner diameter for the center links should be equal to the outer diameter for the inner tubes. Okay. So we don't need this much of thickness. I'm just reducing the thickness to 1 itself. So which is fine. And also you can change the material. For center links, I would try to change the material to some woods or something because it should be rigidly placed in there. So I'm going with spruce or something. Okay, meat and five. Okay, that's fine. And we can place that at the end on 1 centimeter. Yeah, it's fine. So we just place one centering so that the inner tube will stay steady in the body tube. Again, we can select the centerings and duplicate it once more. So we can place that centering little above on the tube in the tubes. So I'm going to change the position towards the more top of the inner tubes. Okay, as you can see, the inner tubes position will changes more towards to the top of the inner tubes. Okay, so top. Yeah, this is perfect. So the component you can see that is the component, and I'm going to okay with this. So right now, um, most of all the basic structures of our rocket is completed. The basic structures of the rocket is completed. We got the fin, we got the nose cone, the body, and we having a stability to 1.16. We can increase the stability. So what we can do for increasing the stability by changing the dimension of the fins, or maybe we can move the center of gravity more upwards. So to move the center of gravity to upwards, we have to use some kind of masses on the top side. Okay, so we can go for that. So what are the mass components that okay? These are the body components that we completely use the body components, and the inner components are there that we have used right now, the inner tubes and the centerings that we have used. Okay, if you want to use the engine block, we can also use the engine blocks here. Then we are going to use the mass components. So the mass components are the parachutes, streamers, shock cords, and the mass components. Like you can configure that. So the mass components are parachute, so which is used for the recovery. Okay, as we mentioned, we have to use the parachute to recover the rocket safely back to Earth. Okay, that's why we have used the ignition, sorry, backfire delay period. So we can just go and add a parachute at the top of the rocket. Okay, we can add, we don't need this. So there is a lot of configuration that we can make on the parachute. What should it placed, or what should be the diameter of the parachute? What should be the thread lines? These the codes. That's the codes that the parachute should have. What should be the thread length? Okay. What should be the material of the wire? We can say this wire. What's the wire material? Okay, let's we can change this here. We will also change the drag coefficients here. Mm, okay, so I'm going to place the so now the parachute is right here, and we can change the position of the parachute to into the body tube. So ignition, after ignition, the parachute will come out. right side. So I'll just place somewhere here. So you can see that the parachute is getting here, and you can change this the packed length or packed diameter right here. So now you can see that the parachute is once there. And also the component mass, the parachute will have a mass. It's shifted the center of gravity. And you can see the materials and everything is just going with this configuration. So there is a slight increase in the stability. And now we need some cords which is connected to the parachute and to the nose cone and to the body. So I'm going to take some show cords. So you can change the show cord's length here. You can change the material. What should be the material? Should the nose the show cord will have? So there is a lot of materials that you can select from here, and also you can add custom materials here. So you can the component mass is shown here. This also slightly changes the center of gravity. So I'm just going to place the show cord below the nose shoulder. So I'm just changing the position from here. So you can see that the position of the nose cord will change. It's changing. So okay, this is fine, I guess. Mm. So now, even if the nose will separate at the apogee, at the top portion, at the highest altitude, that's the apogee, uh, the parachute is connected to the nose cone and also to the body tube. Okay, that's fine. So now we're having a stability of 1.25. For most of the rockets, we will having some kind of mass components. So we can add some mass components like on here. So if you want to use one type of, there is a lot of mass components. As you can see, there is a lot of mass components right here. You can select the mass components and increases the mass at the tip so that we can increase the stability. So I'm just going to use it. There's a lot of components, electronic components like altimeter, flight controllers, and trackers and things. But there is no pre-built-in uh, software support for the electronic components that we can use on the rockets. But however, we can use the mass component to simulate their effect, like how much weight they are going to give to the body, how much weight they are going to give the entire rocket. So you can select a complete mass component and increases the mass some values. Let's say up to 50 grams or something. And so I just selected the 50 grams. I'm going to place that on the nose cone. Now you can see the stability is well over 2.6. The stability is very much increased. Okay. So now we cannot. Is another thing is called a recovery system. So we also use the parachute as a recovery system. to protect the parachute from the heat and hot gases that will come out after the burning of the motors. Okay, to protect the parachute from the heat or hot gases from the motor after the complete burnout of the motors, that we can use some kind of recovery deployment charges there. We don't need that, the recovery hardware. So we can place that recovery hardware below the parachute. So we can place that somewhere here, I guess. Mm, I think it's fine. So now we are basically done a pretty good job. Like we are basically um, created a design for a rocket. Okay, I think it's time 9 p.m. Is everybody's fine with the time? We can wind up the session well we over in 20 minutes or something. Is everybody fine? Is any responses? Hello?
Yes, sir.
Okay. So we can wind up the session in just 20 minutes or something. So basically we just created the design, okay? We're having the basic components right here with the design. So this is the side view. As you can see, there is the view type. This is the side view, and we can change the side view to top view, back view, and 3D figure. So if I change it to the 3D figure, it will load a 3D figure. Then how it's look like, which components, different components look like in the here. So I can rotate it. We can see that there is the fins which is attached to the main body, and there is the center rings. You can see the center rings, right? And there is a nozzle at the below of the motor mounting. Okay, and there is the nose right here. So if we go to the 3D finished view, you can see that our body with the materials that we selected. If you remember that our main body is the cardboard, so the body comes on the cardboard. Okay, so this. Okay, you can see that the fins will made about some type of wood, right? Okay, so we basically created or designed a rocket which may be fly, and you can see about the dimensions and the configurations of the entire rocket. Yeah, this length is 65 centimeters and maximum diameter is 5 centimeters. The total mass of the motor with and with sorry, the total mass of the rocket with and without motors. Okay, and there is the which type of motor we have used, F45 bar 5. So as I mentioned, the F is the total impulse and the 45 is the thrust, how much thrust, and the 5 is the delay period. Which I mentioned, like when the rocket burns out, okay, there is a time lag between the rocket burns out and which pushes a hot gases to the parachute. So that's why we use the meshing here to reduce the impact to the parachute from the hot gases. So that there is a time lag between these two events. That is the delay period that's mentioned here. Okay. And the maximum apogee, which is the maximum altitude that this rocket with this configuration can reaches. It is 397 meters. Again, the maximum velocity and the maximum acceleration. You can say. So it's pretty completed. The complete structure we are completed. We have designed it, and we can just go to the flight simulation. So we having no motors. So this is the first simulation. We don't need that. This is the second simulation. Um, so you can see there is the configuration, that's the motor, which motor we are used for this, and the velocity, the apogee, maximum apogee, and the velocity of descent, I guess, and the optimum delay time, and the maximum velocity, maximum acceleration, time to apogee. Okay, how our rocket is going to perform. Okay, the rocket will get to the maximum apogee of 390 something, as you can see here. Okay, within the time of 7.42 seconds, the maximum altitude is, let's say, apogee 397. Okay, so you can see the apogee, and there is the recovery device deployment. Where will be the parachute will deploy? That's right here. You can see here, and the motor ignition start from zero. The motor burn out. Okay, the motor will completely burn out after 1.5 seconds. But even though it's completely burn out, it will have a velocity, so it gets to maximum approach. After that, it's slowly descent due to the effect of gravity towards the ground after 52 seconds. Okay, that's the time to the altitude simulation. And we can change the parameters to different. If I changes the parameter and x-axis to act on the body. Okay, so the wind, different area of our world have different wind characters, different um, other characters like the temperature change and things. So when we simulate at a particular location, we can also use the launch conditions. On the simulation tab itself, you can see there is the first condition, launch conditions. So here on the launch condition, we can change different parameters. So the average wind speed, standard deviation, the turbulence intensity, the air turbulence intensity is there, and what is the wind direction. Okay, so this type of conditions that particular to a position, and also like there is, you can see that launch site. If we changes the altitude and longitude here, this also changes the flight performance, the performance of the rockets that we are trying to build. Okay, so before we simulate, we have to input the values by measuring and from the site. Okay, we have a lot of instrument to measure the wind speed, the turbulence, and the wind directions. Using that device, we have to measure that and input that value here. So which is the simulation automatically adjusts to that. Okay. I think it's fine. And so there's one more parameter is there. There is the altitude. So there is the altitude. If you want to change, if you want to see so many aspects on the y-axis, you can add new y-axis and you can change the parameter on the y-axis and orientate a lot of parameters. Okay, a lot of parameters right here. So when you download the Open Rocket Simulator, so you have to go for a lot of simulation. Like you try to plot so many variants, so you will minimize. So I want to I need to maximize the apogee, so I can change my fin structures. So how I can change my So I'm trying to. So here I selected the fins. So we have two parameters for the fins, the position and the can angle. So I'm just selecting the position, the can angle. So it comes here. So which says that the current is 0 degree, minimum is 0 degree, maximum is 0 degree. So there is nothing that can do to the cant angle, that is the tilt angle for the fins, which will going to increase the apogee. So I don't have to care about this. So if I go to select the positions, the maximum altitude we get at the minimum or the maximum values. So I can change it. So all the rocket optimizer automatically optimizes the uh, position of the fins of the rocket. So if I selected the second parameter position and I need the apogee, the maximum value, and I comes down here. So we can also give a stability, minimum stability. We can give some parameters right here. So which maybe changes the maximum or minimum values. Okay, then comes here and start optimization. So you can optimize your complete pin structure for the maximum apogee and the maximum altitude. The computer will do its. So it's already in the best value because it's 0, it's already in the best value. So maybe we can try another parameter like the another parameter ground hitting speed. If we want to reduce the maximum, so we have to minimize the ground hitting speed. So I'm trying to minimize the ground hitting speed. So I'm going to select the parachute. Okay. So if I deleted this, I just deleted. I deleted this. Okay. And I'm going to take the parachute and the deployment altitude, deployment delay, and the so I just connected to this portion. And if you want to select or add, it will automatically comes here, and the probability changes by the fins and by adding the weight, and we optimizes and finally we optimizes the rocket for the better performance according to our preferences. So I think we have dealt with the most parts. And if you guys want to get them mastered, okay. So basically, so if you guys want to be master in this, like it's a pretty basic software. I'm going to stop this. So guys, we have done most of the parts as I said. If you want to master in this, what do you have to do? You have to roam into YouTube and you can get a lot of tutorials and you can understand a lot of things more than me. Like I just explained or I just introduced you to the Open Rocket Simulator. You can use so many resources from the Googles. There is a lot of PDFs and you can use the YouTube. So many channels as I mentioned in the presentation. There's a lot of channels which will give you to the intro and make you master in this. So you have to go for that and make yourself master in this. Uh, First of all, you have to download the software from the Google. Okay. And what I'm trying to say is, I'm trying to give you a project, not a project, but what would I say? If you guys have the resources, have the laptop or have the computer or anything, you're trying to do an assignment, as I say, I can say an assignment. You try to do an assignment that I will going to share in your groups. Okay, is everybody fine with that? Can you do an assignment on what we have studied today? Hello.
For your rocket Odyssey, then feel free to share the Google form which you all submitted. The final deadline will be before 14.